Hi there, welcome to this video. My name's John. I am a mathematics tutor and I provide tuition for A-level maths, A-level further maths, 6-term examination papers and mathematics admissions tests. Welcome to this video where we're going to take a look at a problem that I've selected from a past 6-term examination paper, and it's the 2015 Step 1 paper that we're going to be taking a look at here, and it's question 8 from that particular paper. So I'll leave a link in the description to this video so you can download the paper for yourself, and I will show the problem up on the screen various times throughout this video so that you can see the problem as you're watching the video as well. Might be worth you taking notes if you need to from time to time, because I won't necessarily be able to keep everything on the screen. I don't necessarily want to be scrolling up and down all the time, because it wastes time. I'll do it if I need to, but it might be better for you to take notes. Okay, so let's jump into it then. The first few parts of this problem are quite straightforward, to be honest with you, but the last part is the one that caused me the most difficulty. So let's have a look. So actually the first part of this is fairly routine. Show that 1 plus 2 plus 3 plus plus n is equal to a half n times n plus 1. Now, there's a million different ways that you can go about this. The way that I mean, it's fairly routine. It's basically an application of the formula for the sum of the first n terms of an arithmetic series. So hopefully you are familiar with arithmetic series. If you're not, then by the time you get to your step, then something's wrong. So you can prove it that way, or you can prove it by, if you're familiar with proof by induction, you could prove this by induction. And there's nothing stopping, although this was step 1 in 2000. So now there's just the 2-step papers now. Back in 2015, there were still 3-step papers. The first step paper kind of concentrated on just the normal A-level maths stuff. But you wouldn't be prevented from using further maths techniques to solve the problems. Just because the material is solvable, just using the normal A-level maths stuff doesn't mean that you have to restrict yourself to just normal A-level maths stuff. Nevertheless, I think proof by induction, that it's not necessary here. All we need to recognise here is that we've got an arithmetic series. So, arithmetic series. The first term, a, is equal to 1. The common difference is equal to 1 if we need that. The number of terms is n, and the last term, l, is equal to n. So you've got a couple of different formulae, right? You've got Sn equals n over 2 a plus l, or you've got n over 2 2a plus n minus 1 d. Whichever you prefer to use, it really doesn't make any difference as long as you're clear about what you've done. That's the important thing. Just always be clear about what you've done, what your working out is. So using either of these formulae, if I just use the first one, so I'm going to use this Sn equals n over 2a plus l. Then I get Sn equals n over 2 times a, which is 1, plus l, which is n. Oh, would you believe it? There we go. Half n times n plus 1. Easy as that, okay? Throwing marks away. However, that is the first part of this problem. This is typical of a step problem where the first part of the problem, if it's a multiple part problem, the first part is usually fairly straightforward. Okay, sometimes there is a bit of a challenge to it, but other times it's really straightforward. And then once you get onto the next part, that's when things start to ramp up a little bit. Okay, and you've got to think a bit more carefully. Okay, so we're done with that. Let's move on to the next part then. So, part 2. We are going to be using that result, by the way, at some point. Oh, that's something else to bear in mind. If you've been asked to do something bear it in mind because there's a good chance that you're probably going to have to use that result further down the line. Okay, if there are subsequent parts, if you've just done something and there's follow-on parts, be looking for ways potentially to use that result that you've just derived. Don't think that the problems are all just completely isolated and separate problems, because they're not. They mix in with each other. Okay, so if n is a positive integer, so I'll make a note of this. So n is a positive integer. M, lowercase m, is a non-negative integer. So non-negative means that it could be a positive integer, but it also could be 0. So non-negative integer, and what was the final one? And k is a positive odd integer. Positive odd integer. So prove that the expression n minus m to the power of k plus m to the power of k is divisible by n. Okay, so this is really straightforward actually. If you're familiar with binomial expansions, if you're happy with binomial expansions, this is easy. So for example, the binomial expansion n minus m to the power of k is equal to the sum, and you can write it out using sigma notation or write it out in full, whichever. It doesn't make, again, as long as it's clear what you're doing, as long as it's clear to your examiner what you're doing, and obviously as long as what you're doing is correct as well, then that's all that matters. Okay, there might be all sorts of different ways that you can present your solution to a problem, all of which are valid. Obviously, some ways are going to be invalid, but we're not interested in those. So we've got k, choose r, and it's going to be n to the power of k minus r times minus m in brackets to the power of r. Okay, so this is equal to the sum from r equals 0 to k minus 1 of k, choose r, n to the power of k minus r, minus m to the power of r. Now notice what I've done here is that I've just missed off. I'm only summing up here to k minus 1 rather than k. Because what I'm going to do is I'm going to tag on the end the minus m to the power of... Okay, just to be clear then, I'll just write it out in full, that last term. It's going to be k, choose k, n to the power of k minus k, which is n to the power of 0, minus m, r is equal to k in this case, minus m to the power of k. So k choose k is equal to 1. Okay, so we can get rid of that. N to the power of 0 is 1. We can get rid of that. Now, because k is a positive odd integer, okay, then minus m to the power of k is going to be equal to what? It's going to be equal to minus m to the power of k. Okay, so this here, because this is purely because k is a positive odd integer, I can replace that with minus m to the power of k. So I can get rid of the plus sign as well. So it's going to be minus m to the power of k. So please do not think that I'm replacing, that there is general equality between these two expressions. Okay, minus m in brackets to the power of k and minus m to the power of k are in general not equal. but they are equal provided that k is a positive odd integer. Okay, and it's that fact that I'm using. Okay, so this in turn then is equal to... okay, maybe I will write this out in full now. This this summation, this sigma jobby. So what we get is k, choose 0, n to the power of k. So it's going to be minus m to the power of 0, which is just 1. Which, okay, I'll write it in anyway. Doesn't do any harm. Plus k, choose 1, n to the power of k minus 1, minus m to the power of 1. And I'm writing this out really just so you can see more clearly what I'm doing. And we end up with k, choose k minus 1, n to the power of 1 minus m to the power of k minus 1, and then the minus m to the power of k tagged on the end. Okay. So if you notice, we've got a factor of k, a factor of n in each of these terms. So therefore I get equals n times k choose 0, which is equal to 1. I could simplify, but again, just so you can see exactly what I'm doing here. N to the power of k minus 1 minus m to the power of 0. Because what I'm not suggesting here is that this is how you have to present your solution. What I'm doing on the screen here is really to clarify my my method. Okay, how you actually present your solution, that's entirely up to you. Plus k choose 1, n to the power of k minus 2 minus m to the power of 1, and on up to k. So we'll get n to the power of 0 effectively, minus m to the power of k minus 1, minus m to the power of k. Okay, so therefore we conclude that n minus m to the power of k plus m to the power of k is equal to, as we've just seen, n times all of this stuff in the brackets, k choose 0, n to the power of k minus 1, minus m to the power of 0, plus and on k minus 1, minus m to the power of k, minus m to the power of k, plus m to the power of k. So that cancels with that, and so n minus m to the power of k plus m to the power of k, since it has a factor of n, is divisible by n. Okay. And even after all these years, it still amazes me sometimes that algebra is such a is able to express these patterns, these relationships between numbers in such a succinct way. Even after all of these years of dealing with algebra, it shouldn't really surprise me as much as it does, but algebra really is a beautiful thing sometimes. Okay, so that's that done. So now, and we're going to have to bear that in mind, that's going to be a useful result for us. So now we move on to the next part, which is let s equal 1 to the power of k plus 2 to the power of k plus 3 to the power of k plus plus n to the power of k, where k is a positive odd integer. Show that if n is odd, then s is divisible by n, And if n is even, then s is divisible by a half n. And then there's a show further part which we'll come to later. Let's not get too ahead of ourselves. Okay, so we've got to deal with two cases here. One, n is odd, and the other, n is even. Okay, so let's take them one at a time. So if n is odd, then of course n is a positive integer. So I'm making a note of that because what I'm expecting is that the result that we've just proved, this n minus m to the power of k plus m to the power of k divisible by n, is going to be useful. But remember, there are some conditions under which that relationship holds. Okay? That divisibility relationship holds. And it's particularly when n, in that case it was uppercase n, here it's going to be lowercase n, is a positive integer. M is a non-negative integer and k is a positive odd integer. Well, we've got the k is a positive odd integer, and now we've got n is a positive integer. It just happens to be odd in this case, but that there was no distinction made in that divisibility relationship that we proved. There was no restriction on whether the uppercase n in that problem was odd or even. Okay, so the fact that in this case we've got an odd positive integer is kind of beside the point in that respect. That will come into play in a different way. We'll have to be conscious of the fact that n is odd in a different sense, but it's not relevant when it comes to that divisibility property. Okay, so for me, it was kind of obvious what to do here. I didn't have too much difficulty with dealing with this. The only difficulty that had really was actually just finding a way to clearly express what I was doing at each stage. And sometimes this is a lot of the work when it comes to finding a solution to a problem. If the solution only exists in your head, then it doesn't exist at all, for all intents and purposes. A solution is only a solution when it can be communicated. So sometimes you've got the solution, the idea, as clear as crystal in an abstract way in your head. But then actually you've got to work quite hard to find the right way to express that idea that is going to be in a way that somebody else is going to understand. But you have to do this. Do not just present a bunch of symbols on your page. When you're in your exams, don't just write a bunch of symbols all over the page and expect somebody to understand what you're getting at, what your solution is. It's not good form. So what I would recommend is that even when you're solving problems and you don't necessarily expect somebody to end up reading the solutions, if you're just going through them because you enjoy solving problems, you want to practice and things like that, get into the habit of actually writing properly, writing your solutions out properly. That might mean that you've got to you write out a rough version of your solution, and then you go back and you refine it. But do this because you need to get into these habits. If you don't get into these habits, then they won't just appear when it comes to your exams. Okay? How you do in your exam, the habits that you develop before you get to your exam are the habits that you will go into your exam with. So if you've developed bad habits, if you haven't really practiced expressing your ideas, then if you haven't done it sufficiently before you get to your exam, don't expect it to happen in your exam. It's something that it might seem like a minor trivial thing, and yeah, I know you're probably just wanting to get on with stuff, but you do have to learn how to properly express your ideas, and it's something that I have to do now. I don't necessarily expect a lot of people to read some of the work that I do. In fact, I know that some of the work that I do, some of the problems that I solve, nobody is going to read my solutions. But nevertheless, sometimes, not always, I try to write out a proper solution to the problem, because it's good practice, because I've got to keep on top of things like that. Okay, so what I did here was I wrote S in a very particular way. So I wrote S equals, and I added an extra term in that doesn't change the value of S, which is 0 to the power of k. So 0 to the power of k plus n to the power of k. Or more specifically, n minus 0 to the power of k plus 1 to the power of k plus n minus 1 to the power of k plus 2 to the power of k plus n minus 2 to the power of k, and so on and so forth. And okay, I'm going to run out of space here on this page. So this continues. So I've got to think, what I'm doing here is I'm kind of pairing these numbers off. So if n is an odd integer, so I need to know what are going to be the numbers kind of in the middle as I'm working from each side. So we've got 0, 1, 2, 3, to n minus 1, n. I'm pairing the numbers off. But then I'm going to get into the middle somewhere. Which numbers are going to be paired off in the middle? Or is there going to be a single number? I've got to figure this out, right? I've just got to be clear. So just try it out for a few small number cases. So you've got 0, 1, 2, 3. If n is odd, then there's going to be an even number of numbers if I include 0. And which are the two middle numbers? Well, it looks like it's going to be, what, n minus 1 over 2 and n plus 1 over 2. Okay, so that tells me what I need to be writing here, right at the very end. N minus 1 over 2 to the power of k plus, and I'm going to write it, rather than n plus 1 over 2, I'm going to write it as n minus 1 over 2 to the power of k. And since n is an odd number, then yeah, n minus 1 is going to be an even number, so n minus 1 over 2 is going to be an integer. Okay, and you can verify that n minus 1 over 2 is equal to 2n minus n plus 1 over 2, which is n plus 1 over 2. So this effectively is equivalent to n plus 1 over 2 to the power of k, if there was any doubt. So why is this useful? Well, in this case, we've effectively got m is equal to 0. In this case, we've got m is equal to 1. In this case, we've got m is equal to 2. And in the last case, just let me get rid of this junk here. In the last case, we've got m is equal to n minus 1 over 2. So, m, in each case, is a non-negative integer. So, it looks like for each of these pairs of numbers, the way that I paired these numbers off, 0 to the power of k plus n minus 0 to the power of k. This is of the form, k is a positive odd integer, n is a positive integer, and m is a non-negative integer. 1 to the power of k plus n minus 1 to the power of k. K is a positive odd integer, n is a positive integer, m is a non-negative integer. Each of these pairs of numbers is of the right form then. Each pair of numbers say 0 to the power of k or each sum of the pair of numbers. 0 to the power of k plus n to the power of k, 1 to the power of k plus n minus 1 to the power of k, and so on, is of the form n minus m to the power of k plus m to the power of k with... I'm not going to write it all out, so... k is a positive odd integer, n a... what was it? N is a positive integer. Let me have a look. Yeah, n is a positive integer, and m is a non-negative integer. Therefore, 0 to the power of k plus n to the power of k is divisible by n, lowercase n. 1 to the power of k plus n minus 1 to the power of k is divisible by n. And if we continue this, we get that n minus 1 over 2 to the power of k plus n minus 1 over 2 to the power of k divisible by n. So therefore, s, being the sum of these pairs of numbers, is divisible by n. Okay? Simple. Easy peasy, squeezy lemons. Okay, so we've still got the other case to consider. What if n is even? We do a very similar thing, by the way. So write s equals... I want to get it right. Yeah, okay, so we still start with 0 to the power of k. Again, n is a positive integer here, plus n minus 0 to the power of k, plus 1 to the power of k, plus n minus 1 to the power of k. But here we've got a bit of a problem, because if we think about the numbers 0, 1, 2, 3, 4, and we start pairing these off, we get a number in the middle all on its own that we can't pair off. Okay, so the final pair that we can pair off is n minus 1 over 2, n over 2 minus 1, sorry, to the power of k, plus n minus n over 2 minus 1 to the power of k. So this is not, it's not n minus 1 over 2, it's n over 2 minus 1. Okay, just to be clear. No, didn't want to do that. And then finally, if we think about this, 0, 1, 2, 3, 4, 2 is just n over 2. So we get on its own n over 2 to the power of k. So this is really just, this is a very common thing with mathematics, just arranging things in a very particular way to reveal a certain pattern. And sometimes it's just something that you've got to figure out. There's not a systematic routine way of going about it. So you mustn't look at this as being a type of problem, for example, which a lot of people do when it comes to maths, that where they don't, some people just don't get the problem solving aspect of mathematics. They see mathematics as just being a bunch of set methods that you use, and each problem that you get in mathematics is of a particular type, and it has its own particular type of solution, and all you've got to do is just identify which type of problem it is and match it up to its type of solution, and you follow the method and you get the answer. That's not mathematics, okay? Mathematics is about actually solving problems that have fairly unique solutions. Unique problems in many respects. So, this is not a type of problem. This is just a problem. And the fact that it's called a problem suggests that there is a problem. There is something that you have to work at to figure out. Okay? So you have to use your imagination. You have to use your creativity. You have to be original to a certain degree. And that's what you're doing here. So how did I know to split things up in this way? Well, I guess I was motivated partly by what I'd been asked to do in the previous part of this problem. That was giving me a bit of a clue. If you just... if I'd just been given the final part of this problem, s equals 1 to the power of k plus 2 to the power of k plus so on and so on, with k as a positive odd integer, show that s is divisible by n when n is odd, that would be a much more difficult problem because I've not necessarily got certain clues. But nevertheless, it would still be a legitimate problem to do. And it wouldn't surprise me if... it wouldn't have surprised me if that had been the problem in its entirety on this particular step paper. They've been generous here. They've given us a bit of a build up, but I think it would be a perfectly legitimate problem for them to have asked from the outset. S equals this sum without any build up to it. It's going to be a much more difficult problem because you've got to think of the bits that you've been given here to do to build up to this as the preceding parts of this problem. You'd have to figure all of that out for yourself. And I'm not saying that will ever happen on a step exam, but I don't see why not. Depends how much the examiners want to challenge you. Okay, so except for this last term, all of the other pairs are of the right form, let's say. So in each case, we've got k is a positive odd integer. We've got, in the first case, we've got m equals... Oh, why did I write equals there? We've got m equals 0. In the second case, we've got m equals 1. In this case, we've got m is equal to n over 2 minus 1. So in each case, we've got m is a non-negative integer, and although we're using lowercase n here as opposed to uppercase n, lowercase n is a positive integer as well. So each of these pairs, 0 to the power of k plus n to the power of k, 1 to the power of k plus n minus 1 to the power of k, plus all the way up to, let's write commas there, what is it, n over 2 minus 1 to the power of k, plus n minus n over 2 minus 1 to the power of k, are all of the right form. So I wouldn't write this in my exam. I would actually write out, in fact I did write out, I've got it here in my notes, I did write out, are all of the form in part 2, that is k is a positive odd integer, m is a non-negative integer, n is a positive integer. But I'm just going to write here, they're all of the right form, so divisible. Each divisible by n. Each is divisible by n. And also, therefore, each divisible by n over 2. Remember that n is an even number. So if n is an even number, n is divisible by 2. So therefore, each of these is going to be divisible by, if each of these pairs, sums of these pairs, is divisible by n, must be divisible by n over 2 as well. So also n over 2 to the power of k is obviously divisible by n over 2. So s divisible by n over 2. Okay, so that deals with that. So now we move on to the final part of this problem. Final part of this problem, which is show further that s is divisible by 1 plus 2 plus 3 plus up to n. Okay, so this is where you've got to remember what we've done in the first part. Okay. Now, having said that, I couldn't see straight away, and this is perfectly normal, I couldn't see straight away how to use that result from the first part. Because my idea was to, rather than show that s is divisible by 1 plus 2 plus 3 plus up to n, I wanted to show that s is divisible by a half n times n plus 1. Because divisibility is to do with factors, and what we're doing when we write 1 plus 2, the sum of the first n natural numbers as a half n times n plus 1, we're effectively expressing it as in a factorized form. Okay, which is much more friendly when it comes to it's much more useful to us when it comes to determining divisibility to consider factors, really, because divisibility is very closely related, closely aligned to factorization and things like that. Okay, but sometimes you've just got to be prepared to try things out. So there were a couple of things that I tried, first of all, that I didn't expect them to work, but because at the time I didn't have any better ideas, I just tried them out anyway. So I thought, well, okay, if s is divisible by, if I can show that s minus 1 plus 2 plus 3 plus up to n, which equals 1 to the power of k, I'm going to write it in a very particular way, 1 to the power of k plus 2 to the power of k minus 2 plus up to n to the power of k minus n, because this is clearly divisible by 1 plus 2 plus 3 plus n. If I can show that this is also divisible by 1 plus 2 plus 3 plus up to n, then that will imply that s is divisible by this. This didn't really go anywhere. Again, sometimes you just got to try things out just to see what happens. And the whole point of these videos is for me to show you some of the ideas that didn't necessarily work, because even though they don't work in this context, for this particular problem, it might actually give you some ideas for things that you might be able to try in other problems. Because usually the reason that I'm trying these things is because I've seen them work elsewhere, probably at some time, or something similar. I've seen it work, so there's something worth trying there. Okay, don't expect that every attempt that you make at solving a problem is going to work. Sometimes you've got to go through, I've said this many times in many of my other videos, sometimes you've just got to be prepared to try various things out at the risk of them not working. So I wrote this as 1 times 1 to the power of k minus 1 plus 2 times 2 to the power of k minus 1 plus n times n to the power of k minus 1. But like I say, this didn't go anywhere. Okay. So then I thought, okay, maybe try this, because what I was bothered about was this the fact that we've got this factor of n plus 1. When we write 1 plus 2 plus the sum of the first n natural numbers as half n times n plus 1, we get this factor of n plus 1. Well, where's that going to come from? So then I thought, okay, maybe I can try this. S plus n plus 1 to the power of k. This is going to be equal to 1 to the power of k plus 2 to the power of k up to n to the power of k plus n plus 1 to the power of k. And if n is even, again, this didn't work, but it was something that I tried out anyway. So if n is even, n plus 1 is going to be odd. So this will be divisible by n plus 1. And this will be divisible by n over 2. Right? So I was kind of hopeful here. I was thinking, oh, maybe there's something going to work here. But I couldn't get anywhere with that. Because I've got the half n, and I've got the n plus 1. But it just doesn't work, unfortunately. So, never mind. Again, you've just got to try things out. Eventually something will work. So, I had a feeling that I would need to consider the separate cases. So, n is odd, n is even. Rather than trying to do everything all in one step. I had the idea in my head, and it's strange sometimes how things work. That sometimes when things are in your head, it's almost like they're just not as real or as clear as when they're written on the page. Because I had this idea in the back of my mind, which was, if n is odd, I know that s is divisible by n. Well, I need to show in that case that s is divisible by n plus 1 over 2. And if n is even, then I know that s is divisible by n over 2. And I need, in that case, to show that s is divisible by n plus 1. Now, I had this kind of in a vague, abstract sense in my mind. But it wasn't until I actually wrote that out on the page. And this sounds crazy, that actually writing out something that was already in my mind, actually writing it out on the page, what I wanted to do, was the thing that gave me the nudge in the right direction that I needed to go. So I already had this in my mind. All I wrote was, I need to show, and this is literally what I wrote on the page, need to show, if n is odd, then s divisible by n plus 1 over 2. And if n is even, then s divisible by n plus 1. That's all I wrote. Okay? Like I say, even though this was already in my mind at the time, it had already been in my mind for several minutes, but until I actually wrote it out, for some reason it just didn't. It wasn't registering. So this is something possibly to bear in mind. This does happen from time to time. That actually writing something out makes it, in a sense, more real to you. Try it. It might work, it might not work. I'm not saying it will always work. It's just strange sometimes how your mind works. And just taking these small actions, just clarifying things to yourself, is what you need to do. Okay? Okay, so how did this kind of push me in the right direction? Well, let's have a look then. So I actually started with if n is even. So if n is even, Then, if you remember last time, I wrote s equals 0 to the power of k plus n to the power of k, 1 to the power of k plus n minus 1 to the power of k, and so on and so forth. Well, it's based on that exact idea. Except I wrote, instead of introducing the 0 to the power of k, I matched up 1 to the power of k and n to the power of k. 2 to the power of k plus n minus 1 to the power of k. And on and on and on. And so, okay, if we think about this, 1, 2, 3, 4, 5, 6, or whatever. So n is even. I've got an even number of terms. I'm matching them up this time. 1 to 6, 2 to 5, 3 to 4. Okay, so I'm going to be able to pair all of the numbers off. So what I get as the middle two numbers are n over 2. Remember, n is even, so that's fine. N over 2 to the power of k plus n plus 1 minus n over 2 to the power of k. Now, it might have helped, actually, if I'd written these, n to the power of k and n minus 1 to the power of k, in a slightly different way. It'll be clearer what I've done. I've got n plus 1 minus 1 to the power of k. And here I've got n plus 1 minus 2 to the power of k. Because in this first case, I've got m is equal to 1, m is equal to 2. Finally, m is equal to n over 2. So k, in each case, positive odd integer. N plus 1. So it's not n that I'm dealing with really here, it's n plus 1. N plus 1 is an odd integer. In particular, it's an integer, a positive integer. M is a non-negative integer. So therefore, each of these the sums of each of these pairs of numbers is divisible by what? Divisible by n plus 1. Okay? So each of these pairs, 1 to the power of k plus n plus 1 minus 1 to the power of k, divisible by n, because they're all of the right of this form, n minus m to the power of k plus m to the power of k, where n in this case is lowercase n plus 1. So therefore, we've already shown that in the case when n is even, s is divisible by a half n. We've now shown that it's also divisible by n plus 1. So that means that s, and this is not difficult to deduce this, s is divisible by the product of these two numbers, divisible by a half n times n plus 1. And this is from the fundamental theorem of arithmetic in a way. N and n plus 1 are not the same number. Well, they don't have they're not the same number. N and n plus 1, they're two different numbers. So if s is divisible by n, or half n, and s is divisible by n plus 1, then it must be divisible by the product. I'm not going to go into too much detail with that. I don't think I've explained it very well, but it follows from the fundamental theorem of arithmetic. Okay. But we can do a similar thing for when n is odd. So n is odd. Again, it's regrouping things in just the right way. In just the right way. So in this case, we get that s is equal to, again, 1 to the power of k plus, and I'm going to write it again as n plus 1 minus 1 to the power of k plus 2 to the power of k plus n plus 1 minus 2 to the power of k. Now if we think about, if we've got the numbers 1, 2, 3, 4, 5, pair these off, we're going to get 1, 5, 2, 4. This number in the middle is effectively n plus 1 over 2. So we're going to be able to pair all of the numbers off, and the last pair that we're going to get is going to be n minus 1 over 2 to the power of k. Remember, n is odd, so n minus 1 is even, so n minus 1 over 2 is going to be an integer, plus n plus 1 minus n minus 1 over 2 to the power of k, and then finally we're going to get plus n plus 1 over 2 to the power of k. Bingo. Right, so each of these, this, again, they're all of the form n minus m to the power of k. Make sure that you write all this stuff down in a clear way in your exam. I'm not going to bother writing everything out here how I would in an exam, because it would just take too much time, and it'd be a little bit pedantic here, because I'm explaining to you in words, so there's no point in me explaining to you in words and then writing everything that I'm saying. But remember, in your exam, your only method of communication, your only medium of communication is what you write on your exam script. So each of these that I've highlighted are of the form n minus m to the power of k plus m to the power of k, where again n is n plus 1. So therefore each of these are divisible by n plus 1. So in particular, they're going to be divisible by n plus 1 over 2. And finally, this final term is also divisible by n plus 1 over 2. Okay? So therefore, S, we've already shown, because divisible by n, because n is odd, also divisible by n plus 1 over 2. Therefore, S divisible by half n times n plus 1, which is equal to 1 plus 2 plus, maybe I should have written this on the previous part as well, 1 plus 2 plus 3 plus up to n. Okay, that's it, we're done. So, hopefully that makes sense. If you do have any questions about any of that, please let me know. Please leave a comment in the comments section if there's anything that you'd like to add. I will be continuing to upload plenty of videos for STEP and MAT and things like that. If there's any ideas that you have about things that you'd like me to cover in my videos, please let me know. So I'm really wanting to help people as much as I can. But if you could let me know how can I help you? How can I better help you prepare for your exams? So particularly like further maths exams, STEP, MAT, how can I better help you to prepare for those exams? That's what I want to do. So I don't make any money from making these videos. I make them because I want to make them and I want to help people. And I really want to help people as best I can. Okay? It would also be great if you could show your support for these videos, if you do appreciate them, and the time that I spend making these videos and uploading them and everything, just by hitting the subscribe button and hitting the like button. It doesn't cost you a penny. I can only really justify making these videos whenever I've got the support for doing so, because they do take a lot of time to make. This is not meant to be a sob story or anything like that, but they do take a lot of time to make. So it would be really nice if I could, knew that there was some people who were getting some benefit from them and appreciated what I'm doing, which would encourage me to continue making the videos. So hit the subscribe button, hit the like button, share these videos with anybody else that you think might benefit from them. And with that, I'm going to end this video. So thank you very much for watching. Congratulations if you made it to the end of this video. And I will see you in the next video. Thanks a lot.